Constrained optima, I have divided this lecture into two parts. Part one is optimality conditions, and part two is graphical illustration of the optimality conditions. So we'll begin with part one. Optimality conditions. The topics are constrained optimization problem, Lagrangian function, constrained optima, feasibility conditions, complementary slackness and stationary conditions, KKT necessary conditions for optimality, KKT sufficient conditions for optimality. So now let's define a constrained optimization problem minimized with respect to vector x, f of x, where f is a mapping from n dimensions to the real line, subject to two sets of constraints. The inequality constraints are of the form gi x is less than equal to 0, where I is in the set script I, where this is the set of inequality constraints. And equality constraints are of the form hjx equals 0, where j belongs to script E. This is the set of all equality constraints. The constraint optimization problem can be rewritten vectorially in this fashion. Minimize with respect to x, f of x, subject to this is a single vector inequality constraint, and this is a single vector equality constraint. So the inequality constraint is bold G, x is less than equal to 0, where G is a mapping from n dimensions to L dimensions, where L is the cardinality of the set of inequality constraints. Likewise, bold H is a vector function where H is a mapping from n dimensions to m dimensions, where m is the cardinality of the set of equality constraints. Finally, the feasible set or feasible region is defined as the set of all points x such that for all I belongs to script I, gi of x is less than 0, and then for all j belongs to the set of equality constraints, hj of x is equal to 0. So this is the feasible region. The feasible region is where all these conditions are met, the set of all points x where all these conditions are met. Now, suppose the constraint optimization problem entails maximization instead of minimization. So we replace f of x with negative f of x, so we can convert it to a minimization problem. Likewise, suppose we have a greater than equal constraint, gi of x greater than equal to 0, then we can replace gi of x greater than equal to 0 with negative gi of x is less than equal to 0 to convert it to this form. Active and inactive constraints. The inequality constraints gi x is less than equal to 0 can either be gi of x less than 0 or gi of x is equal to 0 for any point x. And these are called inactive constraints and active constraints. Inactive constraints correspond to when the point x is in the interior of the region gi of x is less than equal to 0. And active constraint is when the point x is in the boundary of the region gi x is less than equal to 0. Equality constraints hjx equals 0 is always considered to be an active constraint. The active set script A x is the set of all active inequality constraints union the set of all equality constraints, because equality constraints are always considered to be active. Now let's define what's a regular point. At any regular point, x star, the gradients of the active inequality constraints and the equality constraints must be linearly independent. In other words, if x star is a regular point, then the matrix of all gradients transposed has full row rank. These rows of this composite matrix are the transposed gradients of the constraint functions gi and hj. The first block in this composite matrix contains the active inequality constraints. So the index of each gi here must belong to I intersection A. I is the set of all inequality constraints and A is the set of all active constraints. So the intersection must be the set of all active inequality constraints. And del with respect to x, gi of x transpose is the gradient, that is the derivative of the function gi of x, and del x transpose is its transpose. And the second block in this composite matrix is the gradient transpose of the equality constraints. So if x star is a regular point, then the rows of this composite matrix must be linearly independent. In other words, this composite matrix must have full row rank. Lagrange function. So we have a constraint optimization problem of the standard form. And now let's define what the Lagrangian function, also called simply the Lagrangian, looks like. So the Lagrangian is script L, and it has three sets of variables, x, lambda, and mu, and I'll shortly tell you what they are. And it has three terms, this, and this, and let's look at the terms. The first term is simply the objective function f of x. The second term corresponds to the linear inequality constraints, and each function gi of x is multiplied with a lambda I. Each lambda I is a Lagrange multiplier, also called a dual variable. And so the second term is summation of carried out over all inequality constraints of lambda I gi of x. And for these inequality constraints, remember that the lambda i's, the Lagrange multipliers, should be always greater than equal to 0. The third term corresponds to the set of equality constraints. And so mu j's here are also another set of Lagrange multipliers, also called dual variables. And the third term is summation over the set of all equality constraints of mu j, hj, x. There is no requirement that the mu j's be greater than equal to 0. So mu j's can be greater than equal to or less than zeros. The Lagrangian can be expressed more compactly using vector g and vector h functions. So it's equal to f of x plus lambda transpose g of x plus mu transpose h of x. It has three terms. The first term is simply the objective function that's to be minimized. The second term corresponds to the inequality constraints. Lambda is a vector of Lagrange multipliers, and it has dimensionality L, where L is the set of the cardinality of the set of inequality constraints. And the third term is mu transpose h of x. It corresponds to the equality constraints, and mu is a vector of dimensionality m, where m is the cardinality of the set of equality constraints. Now, before proceeding to identify the conditions for constraint minima, let's define what a minima is in the context of a constraint optimization problem. So a point x star, you can see this figure here, this point x star must belong to the feasible region, and it's a local minimum of f of x subject to the constraints. It's not written here, but it must be subject to the constraints because naturally the constraints are satisfied only in this feasible region. If there exists a ball b x star r, in other words, if there is a ball centered around x star and of some radius r, arbitrary r, such that x, for all x belongs to the intersection of the ball and the feasible region. So we are looking at the intersection of the feasible region and the ball, which is this region here. And within this region, for any x, f of x star should be less than equal to f of x. That is, x star should be the minimum of f of x star should be the minimum of all f of x's within this region. X star belongs to f as a strict local minimum if the same conditions except less than equal to is replaced with a strict less than condition. And x star belongs to f is a global minimum if we don't have to define a ball, but everywhere in the feasible region, now we don't have a ball, so everywhere in the feasible region, we must have f of x star less than equal to f. So this is the entire feasible region now, and x star is where f of x star is, the function is at its minimum in the entire feasible region. Now let's begin identifying all the conditions for local optima of x. So we minimize with respect to x the objective function f of x subject to the constraints with the inequality constraints and the equality constraints. And this is the Lagrangian L x lambda mu, which we just saw previously. Stationary point. A stationary point is x star lambda star mu star, assuming some constraint qualification holds, which we shall look at later. And this is often referred to as the saddle point. The primal feasibility conditions are g of x star less than equal to 0, h of x star equals 0. In other words, this x star must lie in the feasible region because it satisfies both set of constraints. And the dual feasible condition is that the Lagrange multipliers corresponding to the inequality constraints g of x must be greater than equal to 0. This is the same as this requirement here. complementary slackness and stationary conditions. The complementary slackness conditions are like this: lambda star transpose G of X star equals 0. So remember that there are complementary slackness conditions only corresponding to the inequality constraints. So lambda star transpose G of X star is equal to 0 implies that in terms of scalars, summation I of lambda I star Gi of X star equals 0. Which means that for all index I, each term of this summation, which is lambda I star Gi of X star, must separately be equal to 0. Why is that? Now, we know from dual feasibility that lambda I stars are greater than or equal to 0. And from primal feasibility, Gi X star are all less than or equal to 0. So lambda I star and Gi of X star are of opposite signs. Therefore, their product, lambda I star Gi X star, must be less than or equal to 0. Now, since no term in the summation is positive, because they're all, so in this summation here, none of the terms can be positive because they're all less than or equal to 0. Therefore, if the summation is equal to 0, then each term lambda I star Gi X star must be 0. Then we have the stationary conditions, which is the derivative with respect to the variable x of the Lagrangian, the gradient of the Lagrangian, that is, must be equal to 0. Which implies that since we know what the expression for the Lagrangian is, this implies that del f of x star plus summation lambda I del of Gi of X star plus summation mu j del of Hj of X star must be equal to 0. I simply converted this to scalars. And then in terms of vectors, which implies that del x f of x star plus del with respect to x of the vector function g of x star lambda star plus del of the vector function h x star mu star must be equal to 0. Now, we haven't seen what the derivative of a vector function is yet, and that's called the Jacobian. So now let's see what the Jacobian means, the derivative of a vector function. So now let's define the Jacobian of a vector function f. Don't confuse this vector function f with the objective function of the constrained optimization problem, which is a scalar function. That's italics, and this is bold f. And so this function is a mapping from n dimensions to m dimensions. So x, a vector in its domain is x1, x2, x sub n, an n-dimensional vector, and f of x is this m-dimensional vector f sub 1, f sub 2 until f sub n. And its gradient of each of these scalar fi of x is defined as before: partial fi x over partial x1, partial f sub I over partial x2, partial f sub I over partial xn. So this is the gradient of each scalar function fi of x in the vector function. And using these gradients, we can now define the Jacobian of the vector function, which is nothing but the gradient or the derivative of the vector function f of x. So the Jacobian of the vector function f is del f of x, which is nothing but its derivative. And it's this matrix. It has n rows and m columns. And each column is a gradient of one of the elements of the vector function f. And therefore, it is a n by m matrix. Now, we know how to differentiate a scalar a times a scalar function f. Now, let's look at its vector equivalent. So, we want to differentiate a transpose times fx, where x is a n-dimensional vector, a is a m-dimensional vector, and f of x is a m-dimensional vector. And each scalar function, which is a component of this vector function f of x, has its gradient given by this expression here. A transpose f of x is nothing but summation I equals 1 through m of ai fi x. The Jacobian del f of x, the derivative of the vector function, is, we just saw, its columns are the gradients of the scalar components of the vector function. And that's a n by m matrix. The derivative of A transpose F, del A transpose F with respect to x, that's implicit, is equal to summation I equals 1 through m of ai del fi of x, where each del f of I is a gradient, and that is the Jacobian del f of x times the vector A. So what we just saw is that the derivative of A transpose f of x is equal to Jacobian times A, which is del f of x times A. The first order KKT conditions. So we have the constrained optimization problem, minimize with respect to x of f of x subject to inequality constraints. Gx is less than or equal to 0 and equality constraints hx equals 0. The Lagrangian is defined and it has three terms: f of x, lambda transpose g of x, and mu transpose h of x. The primal feasibility conditions are g of x star less than 0, h of x star equals 0. The dual feasibility condition is lambda star must be greater than or equal to 0. The complementary slackness condition is lambda star transpose g of x star must be equal to 0. And the stationary condition is when we differentiate the Lagrangian with respect to x, and knowing that the Lagrangian has three terms, we can differentiate the three terms separately, and that must be equal to 0. From the previous slide, we saw how to differentiate a vector transpose times a vector function, which is the case with this and with this term. So the derivative of lambda transpose g of x is the Jacobian del g of x times lambda, and at the saddle point we put x star and lambda star. Likewise, the derivative of mu transpose h is del h times mu, and we replace x and mu with x star and mu star, which are at the saddle point. Now, if we have greater than equal constraints like this, then we can modify the Lagrangian. We can replace the positive sign with a negative sign. So we have negative lambda transpose g of x as the second term, and the stationary condition will change accordingly. So we have a negative sign here. Likewise, if we have a maximization problem, we can also replace the pluses with negatives as before. There are other ways of handling this equation. For instance, we could still retain the plus signs here, and we could replace the dual feasibility condition with a less than equal to 0 also, but we'll stick to one convention. Now we are in a position to list the conditions for optimality. So we are given the constraint optimization problem theorem. If the regular point x star is a constrained local minimum of the COP, then there exist unique Lagrange multipliers, lambda star and mu star, satisfying the first order KKT conditions. What are the first order KKT conditions? The primal feasibility condition, the dual feasibility condition, the complementary slackness condition, and the stationary condition. So the first order KKT conditions are necessary conditions for optimality. They must be satisfied for x star to be a constrained local minimum of the COP. Second order sufficient conditions for optimality theorem. If there exist unique Lagrange multipliers lambda star and mu star satisfying the first and second order KKT conditions, then the regular point x star is a constrained local minimum of the COP. What are the second order KKT conditions? Simply this. The Hessian of the Lagrangian del squared L x star lambda star mu star must be positive definite. That is the second order KKT condition, and it's a sufficient condition for optimality. And we know the expression for the Lagrangian Lx lambda mu is fx plus lambda transpose gx plus mu transpose hx. Gx and hx are associated with the constraints. Since they are so important, I'll list the first and second order KKT conditions again. So we just saw the first order necessary conditions for optimality, and we saw the second order sufficient conditions for optimality.